Minnesota. And so Sasha will speak about mysterious triality. Sasha, please.
Thank you. Yeah, unfortunately, I will have to speak with a Russian accent because I can't do otherwise. And really, I feel like I'm ashamed to speak with a Russian accent these days, and even to be Russian after those atrocities and this senseless war that our insane czar decided to unleash against a sovereign country, Ukraine. So I'm sorry about that, but
yeah. I was born in Kiev, so
yeah,
I do not feel ashamed to speak with Russian accent.
That's true. Yeah, I was born in Moscow, and that makes some difference. But not everybody in Moscow is with Putin. But unfortunately, too many people are. Maybe not that much in Moscow, not that many in Moscow, but still throughout Russia. So and yeah. But anyway, I want to talk about mysterious triality. This is not what I wanted to talk. I didn't want to talk about politics. I want to talk about mysterious triality. So let me share my screen. Actually, oh yeah, the chat is a link to my slides. Thank you, Lena. Okay, and let me share my screen. Okay, guess now we can see it. Okay, all right. So this is a joint work with Hisham Sati, and it's posted on the archive it was posted in November 2021. And here is what I will be talking about. So, oops, now I should do it here. Okay, yeah. So here is the problem. Once upon a time at Harvard, namely in 2001, Iqbal, Naitsky, and Waffa discovered a mysterious duality. The duality was hinted on surprising connections between algebraic geometry of Delpezzo surfaces, BK. It all goes in series. So there is a series in mathematics of Delpezzo surfaces, BK. Then there is exception. There is also they had been known for a long time to be related with the exceptional series EK of root systems, and what Iqbal, Naitsky, and Waffa noticed was that the physics part of the physics theory, they were looking mostly at D branes in M theory and 11-dimensional supergravity, 11-dimensional string theory, and their reductions to lower dimensions via toroidal compactification. So they were looking at those theories, and those theories are also known to be related to the exceptional, had been also known to be related to the exceptional series EK of root systems. Nevertheless, when they looked at those two relations, they found amazing parallels between some features of algebraic geometry of Delpezzo surfaces and features of those dimensional reductions of M theory. Now, so what I have down below on my slide is something else. I'm saying that the study which actually uses the exceptional series EK of the algebraic geometry of Delpezzo surfaces is actually very classical. For example, in the middle of the 19th century algebraic geometry, it was discovered by Cayley and Salmon that a cubic surface, a general cubic surface in CP3, in the complex projective space, has exactly 27 lines. And as some of you might know, that 27 is the dimension of a fundamental representation of the group or the Lie algebra of type E6. And so it was like known for a long time that this algebraic geometry was related to the exceptional series. Well, maybe not at that time, but the 27 confirms this. I think in the 60s, Manin wrote, my advisor Manin, whose manifest Jan and I attended today. So Manin wrote this book, Cubic Forms, in which he described how basically some features of the exceptional series of root systems, of the exceptional series K, how they play in proven main results of the geometry of Del-Piazza surfaces. So there is this classical math subject, the algebraic geometry of Del-Piazza surfaces. And then there is a classical Lie theoretic or combinatorial pattern, the exceptional series EK of root systems. And then there is a newer theory, physics coming from M theory and 11-dimensional supergravity, which actually also gives rise to the same series with striking parallels. Let me just hint upon a couple of those parallels. So, but first off, let me remind you or tell you what the Del-Piazza surfaces are. So a Del-Piazza surface is a complex, compact smooth surface whose anti-canonical class, negative K, is ample, which means sufficiently positive, roughly speaking. So let me save. I can use my stylus. So those Del-Piazza surfaces are classified topologically by belonging to one of those following types. B0, which is CP2, and B1, which is the blow up of CP2 at one point, B2, the blow up of CP2 at 2 points. Well, those points, those points should be distinct, and so on, up to B8, the blow up of CP2 at a generic 8 points. And there is one outlier, which is CP1 cross CP1, another surface which also belongs to this type of Del-Piazza. It's not, so I said that they're classified topologically, so there's families of surfaces. Well, in the B0 family, there is only one Del-Piazza surface, CP2, and here CP1 cross CP1 is also only one Del-Piazza surface. But for higher Ks, BKs, those surfaces, like the surfaces of topological type BK, have moduli. Namely, those moduli appear from those points that you blow roughly speaking, that they come from those points on CP2 that you blow up to obtain BK. And when those points move, the algebraic type or the complex algebraic type of the surface changes, and when you mod out by the group of automorphisms of CP3 of CP2 on which you blow up points, then you get the moduli space of those Del-Piazza surfaces. But I won't be looking at the moduli space of Del-Piazza surfaces. I will be just looking at those types and thinking of BK as just one Del-Piazza surface of that type. So also in topology, people use, well, in symplectic geometry mostly, in symplectic geometry, symplectic topology, people use this notation CP2 connected sum with K copies of CP2 bar for the blow up of CP2 at K generic points. So from the point of view of symplectic geometry, you can, well, of course, those Del-Piazza surfaces are all projective and Kähler, and so from the point of view of symplectic geometry, CP2, BK may be represented as this connected sum. When you cut out a little neighborhood from CP2, take a copy of CP2 bar the surface with the complex conjugate complex structure, and then also cut out a little ball on it, and then identify the boundaries of those two balls with each other, and you would get a new surface, and this will be one blow up. But then you keep doing this by adding another, by making a connected sum with another copy of CP2 bar, and this way you get a symplectic fourfold, which actually is symplectomorphic to BK. All right, so yeah, this is a picture of blow up actually. So this is, to write down something here. Why is it not showing it? Yeah, that's fine. Yeah. Trying to see if I can get a larger view. I'm using GoodNotes. Okay.
Excuse me.
Yeah. Oh yeah.
So for the you were talking about moduli a moment ago. Are you thinking of these del Pezos as symplectic or as algebraic when you're
As
talking
algebraic, as complex algebraic.
So then aren't the first few toric? You get some rigid examples up till 3, I guess, or 4 maybe. Or is it?
Yeah. The first few are rigid, absolutely. Yeah, but starting from some, I think, maybe from 3. No, from more than 3.
Maybe
4, perhaps 5. Yeah, 5. Okay. Yeah, they will develop some moduli.
Great.
But I'm not going to talk about those moduli. So as I said, I'm talking about just one surface of this type when I say BK. But I'm still talking about the complex algebraic surface.
Thank you.
Yeah, thank you for the question. Any other questions, by the way? Okay. Well, I mean, please interrupt me. I know this seminar is probably less formal than many others, so please feel free to interrupt me, and I will be happy to react to your questions. Yeah, so this is a picture that I stole from Hartshorn's textbook, the picture of a blow up. So this is the original surface, the one that we original surface. It's a little piece, this construction of blow up is a local blow up of a surface at a point, of a complex surface at a point. So this is in the middle, this is the point at which you blow up. Hartshorn was showing this picture of a curve passing through the blown up point on the original surface. And when you blow up, he was showing what happens to this point. So this is on the left, we see the surface, which is the result of the blow up, the result of the blow up. And so you see some things worth noting, like you can see this line, which actually projects down to the point that at which you blow up the surface. And this line is called the exceptional curve or the exceptional divisor, E. That's a standard notation for it, exceptional curve or the exceptional divisor. Then this, well, the map, the blow up map, out of a surface you produce a new surface, but there is a map between them, and this map goes the other way around. That is from the blow up to the original surface, and it's called a blow down map, and it blows down exactly this line E. This line E actually is isomorphic to the complex projective line. So it's just a copy of complex projective line sitting on the blow up, which maps to the point. So all other points of this blow up are mapped isomorphically by phi to the complement to the point at which you blow up. So everything is, or you can also pull back the things from this original surface. For example, you may have I don't know, another divisor, another line, complex line H, which is usually denoted by H. So if you think of this as being, for example, let me put it here, for example, CP2, and this is one of those BKs, but in this case it will be, for example, B1. So the pre-image of this line, if it doesn't pass through the, if you take a copy of CP1 sitting on CP2, which doesn't linearly sitting on CP2, which doesn't pass through this point at which the blow up happens, then it will result in some curve, which you may also think of as a line in a way, which goes through somehow, which lies on the blow up, and this is called the proper transform of H. So this is this H, but on the result of H on the blow up surface, and then this curve that Hartshorne sketched, this curve which has a double point at this blow up point, its proper image is this curve over here, in which you can see that its singularity, its double point, is resolved. It's no longer singular. So this is blow up is a common way to resolve singularities, to construct resolutions of singularities. Okay, yeah, so but what I wanted to point out is that on the blown up surface, we immediately acquired two interesting divisors. H, the class of the hyperplane, well, H tilde, but usually we don't denote it by H tilde in this business, we just say H for its proper image and proper transform, and then E, the exceptional divisor, the exceptional curve. So in this case, they both are isomorphic to CP1. They're just copies of CP1 sitting in the blow up B1. Okay, so this is the algebraic geometry we deal with, and then B2, B3, B4, and so on are obtained by blowing up more and more points on the results of the previous blow up, which you can combine into a blow up at several points of the original CP2. And then there is this outlier CP1 cross CP1, which I talked about at first. Now, there is this schematic picture, which actually looks like the E10 Dynkin diagram for those blow ups of Del Pezzos. So if you start with B0, which is CP2, and you do a blow up, you get to B1. And then, of course, you get to B2, to B3, and so on. It starts getting boring, but actually there is another really blow up relation between surfaces, and this is called, and this one is as follows. If you blow up a point on CP1 cross CP1, then you will obtain B2, the same surface as the result of two points blown up on CP2. And actually, yeah, and then it goes on, you know, so this outlier is still related by a blow up to one of those Del Pezzos, B2. And then it goes on to B8. So this is a diagram with 10 nodes and certain edges between them. Okay. Now in physics, there is a similar diagram, but that one is related to those dimensional reductions of supergravity on a K-torus, or they call it Rapin, the 11-dimensional gravity on a K-torus. And also they are known as toroidal.
K is the same as BK?
Yeah, K is the same as BK. And so you start with M theory, which is defined.
We do not know what is it. No?
What? Say
Which
it
we
again?
do not know what is it. What is M theory? I have no idea. but we can start with it. That's okay. But
Yeah.
I don't know what is it.
Yeah. Well, I probably I don't know more than you do about it either. But nevertheless, it's so I'm basically now at the moment I'm reviewing what Iqbal, Knightsky, and Waffa described. So they describe those M theories. So it's some 11-dimensional theory, physical theory. Well, M theory is quantum field theory in 11 dimensions, but it's based on classical field theory, 11-dimensional supergravity. Then if you do this, what they call dimensional reduction, then they get to type 2A string theory in 10-dimensional space. Sometimes the dimensional reduction goes as just modded out by an action of S1 on the 11-dimensional spacetime. So these are the 11 y of 11 dimensions, x of 10 dimensions are the spacetimes of the corresponding theories. Then you can still proceed with dimensional reduction, and you get 9-dimensional supergravity, or if depending on what you're interested in, you may be talking about 9-dimensional reduction of M theory. M theory is still in 11 dimensions, but you can talk about its dimensional reductions. And then to 8D supergravity, right, as G, and so on, down to 3-dimensional theory, 3-dimensional supergravity. Nobody wants to go down below that, probably because maybe going down to 3 dimensions is even an overkill, because the most standard dimension of the space-time I believe in is 4-dimensional rather than 3. But nevertheless, they discuss 3-dimensional theory as well. And now there is also the corresponding outlier. Yeah, no, actually, those lines in physical theories may be thought of as dimensional reductions, but they may be actually formalized mathematically as modded out by actions of S1. So on this X10, you assume to do a 9-dimensional supergravity, you assume that S1 acts on this 10-dimensional space. Another copy of S1 acts on this 10-dimensional space.
My knowledge of M theory is almost zero. I understand that S1 is a part of this 11-dimensional, what you call space-time. It's like something which can be a product of Calabi-Yau cross C squared cross this S1. But how do you do the further dimensional reductions? I have no idea. My physics education.
I have some idea. One simplification, I'm not sure it's totally. I'm not sure that it's the most general way of dimensional reduction, but one way is you assume that there is an action of a high-dimensional torus on the 11-dimensional space, and to reduce on this torus, you mod out by the action of this torus. And so this you're right that this 10-dimensional space may be thought of as well, if you're talking about type 2A string theory, then you should assume that it's further that it's a product or maybe a bundle over the classical space-time R4 with fibers being Calabi-Yau three-folds, complex Calabi-Yau three-folds. But those ones are I mean, the lower dimensional ones are further quotients by actions of S1, and those actions may not be, I don't know, may not be obvious. In the paper of Iqbal, Knightsky, and Waffa, their 11-dimensional space, they only dealt with flat geometry. And nevertheless, they found remarkable things about the relation of those theories in flat space, in flat space-time, remarkable connections to Delphi surfaces. So they were working with Y11 being equal to just R11, and then to get, of course, S1 doesn't well, they didn't mean to be S1 to be acting there. They just said, they coded those this sequence of spaces that of lower dimensional spaces that they obtained from the 11-dimensional space-time R11. They code them compactifications of the 11-dimensional space-time. And what they did is
maybe in order not to be in the position when one blind person leads another one, which is also blind, maybe we'll kind of skip details of physics, because physicists will probably, if they would like, will listen this recording, they will laugh. So
probably, I totally agree with you.
But it's better kind of to
but it's easy to say what they were doing. Like they had R11, then they said, okay, let's do R10 cross S1 by compactifying one axis, like the X1 axis. Then they said, okay, let's compactify the other axis, like X2, the X2 axis, by adding a point at infinity. And this way they produced R9 cross S1 squared. And then they removed this S1. So in their case, it was a very trivial, like Cartesian product situation. So I and V refers to Iqbal, Naitsky, and Waffe. So this is what they were doing. Okay, but a little bit more general picture is modeled out by actions of S1. Yeah. So, all the physicists
actually, there are many, as for E10, yeah, E10 is remarkable. But if it was something like E6, E7, E8, there are hundreds appearances of Dynkin diagrams in mathematics, so in physics as well. So what's the point?
Yeah. The point is not just those diagrams, even though I was still planning to sketch another collection of diagrams. So they found deeper relations between Del Pezzo surfaces and physics. But actually, on this slide, I wanted actually to. Well, let me skip, since you asked this, let me skip this slide for the time being and return to it, because this slide explains how in the geometry of Del Pezzo surfaces, the EK series arises.
Yeah, but this is mathematics. So maybe
this is pure mathematics. Physics is here.
Yeah, no, but maybe we better look at mathematics. We can understand something. It's not a configuration of curves in the exceptional divisor, because it looks like a 6, a 7, A8 only for last B6, B7, and B8 when you blow up 6, 7, and 8 points.
Yeah, absolutely.
So then you have 6, 7, and 8 CP1s. Probably, something like that. Is it just the intersection of this? No, it's not, because you are.
It's not quite in the intersection, but it's related.
Take orthogonal complement to the. It's Fana to the first Chern class of canonical. Okay.
Yeah.
And the pairing is just Poincaré.
From what?
Poincaré pairing.
Yeah, absolutely. Yeah, it's the intersection form. Yeah. Right. Yeah. So here's actually a picture which happens inside mathematics, which is actually fascinating, which actually was the main reason why I got hooked on looking at this topic. So 1, 2, 3, 4, 5, 6, 7. So if you take the diagram of the Dynkin diagram of type E8, then and start cutting off pieces of it and looking on the left, on what's left on the left, starting from, well, of course you can start with this, and then what you are getting is a smaller a smaller rank Dynkin diagram, And so if you start with this cut, you get E8, nothing happens, you don't really cut it. But then for when you cut it once, you get E7. When you cut it twice by the slanted line, you get E6. When you cut it one more time, look what was left on the left. You've got the Dynkin diagram for D5. All right. Now, when the next cut gives you A4, the next cut, and this is why those lines were slanted, gives you A2 cross, which is called, well, just the joint union of two Dynkin diagrams, but it corresponds to A2 cross A1.
So how did you cut? I'm confused.
I'm
Because
cutting
when
at
you cut, I see
45 degrees.
I see A2. Yeah. A2. Why product
A2 and A1. Yeah,
when,
because if I cut here, so
this vertex remains.
what remains is this.
Yeah. Okay.
Right. Yeah. So this way you get A2 is the corresponding root system is called A2 cross A1. Then there is no way to identify this case, but P1, but down there you get the next cut leaves you nothing and still nothing for the next cut afterwards. So this is this, but well, you can figure out that the root system that you obtain by this procedure, which is taking the second integral cohomology group of BK and computing the orthogonal complement to the canonically defined M element of it, which is the canonical class or the first Chern class of the canonical class. And then identifying the EK root system within this orthogonal complement, then you will be obtaining those diagrams, those types there. So not only in the theory of Del Pezzo surfaces, but in other subjects, in representation theory, for example, it's common to call the series that you obtain, well, usually it starts with A1 over here. It's common to call this EK. All of this, even though the true EKs show up only for K equals 6, 7, and 8, as you pointed out. But these are what EKs turn into in those when K becomes smaller. Okay, so this is the basically sort of a short way to describe how the root system of type EK arises in the context of Del Pezzo surfaces. Okay, so this is this, and now in physics, what these people, Iqbal, Naitsky, and Waffa found out that they found a little bit more interesting relationship between Del Pezzos and brains in physical theory. So here, this is just one example of one-dimensional reduction when you get a type 2A string theory by reducing one dimension on 11-dimensional M theory. And here we have to be talking about B1, the Del Pezzo surface B1, the Del Pezzo surface B1. And you look at those homology classes. And on the other hand, here they put in correspondence by looking at brains, different brains in, well, like brains coming from membranes, roughly speaking surfaces, but usually they come with some other structure, such as a metric or some fields on them. But let me just think of them as surfaces in space-time, here in 10-dimensional space-time. So there are different brains. They have names like D0 brain, F string, and so on. NS5 brain is for Never-Schwarz brain, and so on. So they looked at those brains and looked at some physical quantities associated to them called tension, brain tension, tensions for those brains. And if you look at the structure, I guess you again, yeah, I just picked this a table from the original paper of Iqbal, Naitsky, and Vafa, and I didn't make any changes to it. I just took it as a picture. So really, what I understand somewhat is this left-hand side of the brain tensions. Look how parallel it is to what you have on the left-hand side. It's still just combinatorics, just some kind of numerical coincidences. But if you think of R as being related, R inverse related to E in those brain tensions, and LP negative cube to be related to H, then you can see that these tensions sort of prescribe what kind of homology classes you have to consider. So they have this mnemonic rule, which they pointed out, but again, they said these are the standard types of brains.
E is an exceptional divisor for B1 or what?
E is the exceptional divisor, and H is the class of the CP1 coming from the original CP2. So this is exactly why I sketched this picture. So that's H. Well, and it's on B1 it will be that, and E is that. Yeah. Right. And so they said, well, these are our favorite brains, D brains, and they have those tensions, and those brains correspond to those homology classes. They said correspond to. They didn't know. They never pointed out why they correspond to to those homology classes. They just said, well, yeah. Another thing is that if you work with those brains, then you create a similar. You can identify roots and of type EK and similar Dinkin diagram just from those D brains, and the corresponding diagrams work on the side of the Delpezzo surfaces. So this was their remark. But the thing is that they called it mysterious duality because they actually didn't know how it works. That is why this correspondence. It was purely combinatorial. It was like identifying things which look similar. Like you take this, and so it means you have to take negative 2e because it's r squared, and then LP to the negative 9 is 3h because it's because negative 3 corresponds to just h, and this the r is the radius of the circle S1 by which they mod out. That was also a parameter in the physical theory, and LP is the Planck scale. So it also had some certain physical meaning, which is beyond me. Okay, and so they said they basically said here is mysterious duality, but one needs to discover this mystery. Why physics and algebraic geometry give rise to those EK series without pointing out any explicit connection between physics and algebraic geometry. Since then, there were several attempts, like how would people to create a connection, to construct a connection. For instance, I mean, one of maybe most naive idea, but people tried it, is associate to a Delpezzo surface a physical theory, like to write down its Lagrangian, its fields, its fundamental fields, and so on, to define this physical theory, but sort of coming from the Delpezzo surface. But it never worked out. Nobody had known how to do it. And I should preempt the question that we don't know how to do it either. But we know something else, which we found also remarkable. Namely, this is what we've done. So this part on the left-hand side is the original Iqbal, Naitsky, and Vafa relation from 2001. And what we did with Satya was to create a sequence of topological spaces and look at their rational homotopy types. So we worked in the framework of algebraic topology, but kind of simplistic algebraic topology known as rational homotopy theory. And we found a sequence of topological spaces whose rational homotopy types were directly related to the EK series, and at the same time those rational homotopy type are also explicitly related to physics, to those k 11 minus k dimensional supergravities. So let me write here that this part, and I put the two arrows in this diagram as dotted arrows, and this as a solid arrow. And the thing is that what we have here is, I wanted to emphasize that what we have here is an explicit connection between physics and algebraic topology. And I think I will, even without the knowledge of physics, expected I will be able to explain this connection to you. I hope I will be able to explain this connection to you. So the main results of my talk and our paper on the math physics side, so we have two types of results. One is mathematical physics, the other one is mathematics. So on the math physics side, the statement is that the rational homotopy theory, RHT, well, now I'm disclosing what those spaces are, of certain iterated cyclic loop spaces of S4, of the four-dimensional sphere. The rational homotopy theory of those spaces is explicitly related to the M theory story. So here's what I mean by an explicit relation. So for instance, if you want to write down the equations of motion on M theory wrapped on T5, well, just the equations of motion of supergravity, which would give you six-dimensional supergravity. Believe me, those equations are complicated. It's like several basic fields that you deal with. Of course, it comes out of a certain equation.
Compactified or what? There was no.
What is compactified?
No, what is wrapped on T5? M theory lives in 11 dimension, and you compactify it, if I remember your terminology, by T.
Yeah.
So
yeah.
it means compactified on T5. Yeah.
Well, it was in Iqbal, Naitsky, and Waffa that they dealt with compactification because they were doing this sequence of spaces. They first compactified, then they removed the S1 factor. This is how they were doing it. But we are thinking that this 11-dimensional space is just any 11-dimensional real manifold, and then with an action of S1, and you get the 10-dimensional dimensional reduction, or they call it in physics also toroidal compactification of 11-dimensional theory to 10 dimensions. And then you again assume that there is an action of S1 on this.
Yeah, that's okay, but
spaces.
there is no word wrapped here, and wrapped in physics means something different. So that's
not necessarily. It's actually wrapped means divided by S1 by an action.
Okay, so are you sure that they use that terminology?
Right. For brains, they say, like, when they obtain, for instance, let's say some of those brains come from yeah. So you get if you do just the original 11D supergravity, then you would be having just the M2 brain and M5 brain. And when you wrap those on the action of S1, so those which correspond to E and 2E. Sorry, there is no exception. Sorry, H and 2H. In this correspondence between algebraic geometry and physics. So when you wrap those brains, M2 and M5 brains, you obtain 1 and 4 brains. So which ones here are 1 brains? Yeah, so this is wrapped on S1 is the F string.
Mm-hmm.
And this one wrapped.
I should regret that I
D4.
asked you that question, because it's not really, I don't think that this will help, and I don't think that people will enjoy this physics.
Physics speak. Okay, sure. I don't want to do anything
Yeah,
that
yeah,
you
yeah.
wouldn't enjoy.
My mistake.
No, that's okay. Yeah. So where are we? We were here, right? Yeah. So okay, wrapped or whatever, compactified. You can say compactified here on, or modded out, factored by T5. So get into the 6-dimensional supergravity, and there are lots of fields, lots of complicated equations between them, the equations of motion, and nevertheless, you can just read them off from the rational homotopy theory, namely from the differential in the Sullivan minimal model of this 5-fold cyclic loop space of S4. So this is a math physics statement, a result, namely we develop, we describe an explicit connection between the rational homotopy theory of this series of topological spaces, k-fold loop spaces, cyclic loop spaces. I will tell you more what those are on S4, and the equations of motion of supergravity, of lower dimensional supergravity theories, namely 11 minus k dimensional supergravity. The mathematics result is that this series of topological spaces, S4, the 4-dimensional sphere, and its what we call cyclifications, so cyclic loop spaces or cyclifications. And so like L2 and so on, they are iterations of this cyclification procedure, which I will describe in the next slide. So the series of spaces is another series of objects with hidden internal EK symmetry, just like those Del-Pezzo surfaces. So as Jan said in the very earlier, there are lots of objects in mathematics which give rise to the EK series, and here is a new one, which shows up in topology. And for example, you get amazing things in this context, like you can identify 27 lines in this topological space, the 6-fold cyclification of S4.
Sash, what do you mean saying that they have EK symmetry? So these are some topological spaces. Is it the action on the rational homotopy type, or on what? EK acts on what?
Yeah, so I said hidden internal EK symmetry. EK, so we don't really know whether EK acts on those spaces except for lower dimensional K, like for K, exactly those which are shown up here, K equals 0, 1, and 2. But what we know is, this is why I called it hidden internal symmetry, is that it's, for the Del-Pezzo surfaces, they also don't admit an action of EK. There is no known, at least interesting action of EK on the Del-Pezzo surface BK. Nevertheless, they hide some EK symmetry. For example, the Weil group of EK acts on the roots. The roots correspond to certain distinguished divisors or elements of the second cohomology on those Del-Pezzos. So there are lots of things which are related. And for instance, in the case of B6, the famous 27 lines show up there exactly because of this fundamental representation of E6 as well. So there is no direct action on anything in relation to Del-Pezzo surfaces. Nevertheless, there is some symmetry pattern, maybe combinatorial part of it, like the Weil group action. There is a Weil group action on the Picard group or on the second cohomology of BK with integral coefficients. Yes, there is a Weil group action.
On behalf of some people in the audience, maybe I ask on the derived category of coherent sheaves or what?
That's a fantastic question. I actually asked the same question a couple of weeks ago when David Favero came to give a colloquium talk in our department. And I asked him about exactly the same, like, is there, he was talking about Del Piezzo's because, he's interested in the derived category of coherent sheaves on Fano varieties. And I asked him whether there could be an action of EK on the derived category. And he said, that was a great question. And he was thinking about it. He even promised to look at it. Yeah, so we don't know. There might be something like that there. Yeah, so what we know, we're looking at, and what we hope that there is something, is an EK action on the rational homotopic type of those spaces. It looks like this is plausible, but we don't even make it a conjecture because it's not. We have too little evidence, because for those little k's, look what those EKs are. Those are A-1, like SL0, SL1, and SL2, if we are looking at B0, B1, and B2. So that's not very much data to start with to make a conjecture on. Okay, right. So, but we find those objects which give rise in a similar way to algebraic geometry, to the Del Piezzo surfaces, which give rise to the EK root system and to other traits of EK symmetry, but not a complete EK symmetry, or at least conjecture. We don't know. Okay. Other questions?
I'm sorry, I think I missed some. With when you say EK action, are you talking about the Weil group action, or are you talking about the Lie? I mean, when acting on a category, for example. Yeah,
I was thinking about the action of the very algebraic group EK.
Okay.
The Weil group is known where it acts. It acts on the Picard group of the Del Piezzo surface in the Del Piezzo story, and here we also know where it acts. It acts actually on the weight space that is associated to toroidal symmetries of those topological spaces, well, of the rational homotopic types of those spaces. So there is some action, including the Weil group, but not on those spaces, on something associated to those spaces. Okay, other questions?
I have more of a comment than a question.
Sure.
So if Weil group acts on something like homology, then it's not reasonable to expect it action on the derived category. There could be braid group action on the derived category, but yeah. Yeah, but were you talking about the algebraic group action on the derived category, and then in what sense? Like, maybe I misunderstood your comments about.
Yeah. I was thinking about the algebraic group acting on the derived category, but because I thought Jan's question was about that, right? But if you're right that if you expect if you know that the Picard group is acted upon by the Weil group, then we should expect the Weil group hopefully extending to an action on the derived category.
I would say no. There are many examples where Weil group acts on the Picard group, but it leads to a braid group action on the derived category.
There's a shift that occurs, I guess, right?
Yeah. I mean,
it's just that the composition of two square of the reflection is no longer trivial.
I see. So it's the Weil group corresponding of the same type as the braid group of the same type as.
Yeah, it is an exciting question whether there is a corresponding braid group action on the derived category, and it's very interesting.
I see. Yep. I see. Yeah, so maybe it's an overkill to hope that there is an algebraic group action, because indeed those objects are more like, well, in a way you can expect them to be sort of coming from or generalizing the Picard group. So probably indeed on the derived category you can only get something like the while group action. And thank you for the remark. I didn't know that that it was extended to a braid group action.
Thank you.
But even then, even in that setting, this should be sort of on the canonical bundle of the del pezzo, right? I mean, you want to turn these exceptional objects into sort of spherical objects. Is this right? I mean,
yeah, probably. But
on the canonical bundle, but why is it on the canonical bundle? I mean, when you consider the derived category,
Do you mean
he wants to convert them into spherical objects, and so you should take the total space of the canonical bundle first.
oh, I see.
It will be rather colladial.
On the total space, I got it. Yeah.
that makes sense.
Yeah, this makes sense again because of this thing that EK happening in the orthogonal complement to the canonical class, and so maybe you need it's not surprising that there might be some correction related to the canonical class when you do those things. Great. Yeah. Well, I will. That's definitely very exciting what you're telling me. Thank you, Rina and Jan and everybody. Yeah, it's really great. Yeah, I will definitely take a look at this part. So this probably will lead to other wild guesses, but I'm not talking about wild guesses today. As I said, like this action in EK that we expect is too much to even conjecture. So I'm not saying that there is some EK symmetry on the rational homotopy type of these spaces, but it could be. Okay, so this is sort of, so this is basically a summary of the main results. And it's not really, they're not worded mathematically here. It's just indications of to which ballpark those results belong to. Those results belong. Okay, so yeah, but you know, there are remarkable things. We can get 27 analogs of 27 lines on in the six-fold cyclification of S4. We get, moreover, there are some 28 bitangents in L7C S4. So there are remarkable things, well, again, analogs of bitangents, remarkable things that we identify in the rational homotopy types of those spaces. Just going by analogy, by going by the fact that there is some something, that the root system EK is there. Okay, so here are those cyclic loop spaces. So the free loop space of the topological space is basically this LZ. You consider all possible continuous maps from S1 to Z. So you take a standard copy of S1 in the plane and look at all possible maps to your space, target space Z. Now, of course, it means a natural action of the group S1 by rotating the loops, because this S1 is the standard copy of S1, you know, where it begins, it has a parameter, like the angular parameter, or whatever parameter you wish to take, is the standard copy of S1. And so you can rotate this S1, and this changes the map. And so there is an action of S1 on this space. And by modding out by this action, but taking the homotopic quotient by this action of the free loop space, we get this cyclic loop space. So well, for instance, one way to achieve the homotopic quotient is to use the Borel construction, to multiply by a copy of ES1, on which a contractible space on which S1 acts freely, and mod out by, take the product and mod out by the diagonal action of S1. So, and this is this cyclic loop space that I'm talking about. So you might think of this space as actually the space of unparameterized loops. So you can think of points there are indeed loops, but in Z, yeah, so I should have sketched a loop in Z. Loops in Z, but up to reparameterization. This is because the group of diffeomorphisms of S1 is actually homotopy equivalent to the group S1 itself, so diff S1. And so from the point of view of topology, there is no, yeah, I guess you should take plus the orientation preserving diffeomorphisms of S1, self-diffeomorphisms of S1, and this group is homotopy equivalent to S1. So from the point of view of topology modeled by S1 or diff S1, diff plus S1 doesn't matter. Okay. Is there a question? So, yeah. So you can think of this space as the space of unparameterized loops. Sometimes they're called, there is another name for them. We call them cyclic loop space, cyclic loops, or cyclification of Z. Some people call them unparameterized loops, and some people call them equivariant loops. Okay, so we then move on to consider for every k greater than or equal to 0, we move on to consider those iterated cyclic loop space or cyclifications LK sub C of Z. And here's so the formula for LKZ. Yeah. All right. So we'll be interested mostly in the iterated loop spaces for k between 0 and 8. And I will give you an indication why we are interested in those later on. But in principle, they exist for any k. Just like just like surfaces that we obtain from blowing up points on CP2, those surfaces you can keep blowing them up. You can still keep going and blow up those surfaces at as many points as you wish. The thing is that for k greater than 8, the surfaces bk are no longer Del-Pezzo surfaces. They are of different type. They are no longer Fano. So Del-Pezzo surfaces in general are described as Fano varieties of smooth Fano varieties of dimension 2. Okay. So here something happens as well for k greater than or equal to 8. Go greater than 8, and I will tell you later what it is. Okay, now, so we define those topological spaces. For every topological space Z, we can associate this loop space and cyclic loop space, and then we can iterate the construction. Now, I want to look at the key to obtain the structure we're interested in is to look at the rational homotopy theory. So in principle, rational homotopy theory is, you say that two spaces are rationally equivalent if they or have the same rational homotopy type, if there is a rational homotopy equivalence of, well, here I wrote path-connected spaces. So continuous of path-connected spaces. Right, yeah, so let's assume that they're path-connected. So continuous map inducing an isomorphism on rational homology. Okay, and the rational homotopic category is topological spaces with in which localize basically at rational homotopy equivalences, in which we assume that rational homotopy equivalences have inverses. We formally add those inverses. So this is the rational homotopy category, and an equivalence class in this category is called a rational homotopy type. Now, this is basically a story of success in algebraic topology, because you can create objects, algebraic objects that completely characterize those rational homotopy types of spaces. And and this was done by Quillen in the works of Quillen and Sullivan in the 60s and 70s. Namely, the upshot of their constructions is that the rational homotopic category, well, I want to have to say of good enough spaces, is equivalent to a category of differential graded commutative algebras or differential graded Lie algebras. So commutative algebras is the Sullivan story, and differential graded Lie algebras is the Quillen story. So there is this minimal model. I will be looking at DGCAs and the Sullivan models. So the Sullivan minimal model is a certain differential graded commutative algebra associated to a topological space, and this differential graded commutative algebra called the Sullivan minimal model is unique up to isomorphism. Okay, and it classifies the rational homotopic type up to isomorphism. So basically, the two categories are equivalent: category of topological spaces up to rational equivalence, well, good enough topological spaces, and the category, well, it should also be good enough algebras, differential graded commutative algebras up to isomorphism. Okay, and there is a similar story on the Quillen side with Quillen minimal models, which live in the world of differential graded Lie algebras. And also one remark is that we will use R in place of Q. Rational homotopic theory deals with Q coefficients, and this is called rational homotopic theory over the reals. You can take it, actually, it works over any field of characteristic 0, okay? Any extension of Q. That's rational homotopic theory. All right, so this is how these are examples of those Sullivan minimal models, so that you folks know what I'm talking about. For example, oops, yeah. So let me see. Yeah, the Sullivan minimal model of the four-dimensional sphere S4. So how to get that and what it's related to. It's a very simple algebra. Those Sullivan algebras, Sullivan models are supposed to be free as graded commutative algebras. If you forget the differential, they are free. So they're polynomial algebras, in other words, on even and odd variables. And this one is the polynomial algebra with real coefficients, freely generated by two variables, G4 and G7. The degree of G4 is 4, the degree of G7 is 7. And then the differential is determined on its action on the generators. And so dg4 is 0, G4 is closed, declosed, and dg7 is given by this formula. This formula is kind of, there is a funny coefficient. If you've seen this ever in your life, this is actually the first exercise you do when you study rational homotopic theory. Like, what is first RHT exercise? What is the Sullivan minimal model of S4? Well, actually of spheres of Sn for any n. And it turns out that for even dimensional spheres, those Sullivan minimal models are just like that. They are generated by a class of dimension n, of degree n, like G4. I'm talking about even dimensional spheres, which is closed, and then G4 squared will be equal to the differential of some other generator of appropriate degree with some coefficient. Usually you can, in mathematics, you take this coefficient to be equal to 1. Those algebras, whatever coefficient you put here, will be isomorphic as differential graded commutative algebras. But we are using this -1/2 for the sake of relation to physics, which we'll see in a sec, which is actually on this slide below. Yeah, so, but how do you obtain those models? I mean, let me give you the gist of sort of the idea of the story. The idea of the story is that a Sullivan minimal model is an algebra which satisfies certain conditions, a differential graded commutative algebra, it has to be free on some, well, it has to be free as a differential graded algebra, commutative algebra, sorry, as a graded commutative algebra. And in the case when it's simply connected, when there is nothing in degree 1, then, which is the case here, there is no condition which explains the word Sullivan. Sullivan in general is a condition, but the minimality condition is that the differential is split, or decomposes. That is, the differential of a generator decomposes as a product, as a polynomial in lower degree generators, roughly speaking. And so, and then you want to find such an algebra. You just want to guess what this algebra is, such that it has a quasi-isomorphism, that is a morphism of differential graded commutative algebras with the drum algebra of S4. So this is the drum algebra of S4. You want to find an algebra of this type that is free as a graded commutative algebra with a decomposable differential, and in this case, simply connected algebra that is having nothing in degree 1 equal to 0 in degree 1. You want to find a map from this algebra to the drum algebra with a quasi-isomorphism, and this will be, if you find such an algebra, then this is an answer. This is how you do this exercise. You can, if you have spare time, you can do it for other spheres. See what you get. For odd dimensional spheres, the answer is different.
Can I just try to understand the rational homotopy is about the homology group. So for this S4, the homology,
right,
that appears in the degree 4. And
yeah.
This looks to be the kind of a Koszul or Tate resolution of the homology. Am I right? So that's always a great commutative algebra.
You're right. Yeah. It's like the Koszul resolution of this. But yeah, and it's clear like how to construct this. Like you can take any volume form in G4, any closed form which creates on the sphere S4, which well, of course, it's automatically closed if it's a 4 form, but you want to take a form which generates the 4-dimensional cohomology of the sphere. But then if you want and then you create a differential graded commutative, a graded commutative algebra, which is, yeah, you want actually DG4 to be equal to 0 in your algebra. So you create this algebra, but which is just generated by G4. But then you see that this algebra has excessive cohomology, like G4 squared will be a non-trivial element, and it's also closed. So you want to kill G4 squared, and if you just add one variable which kills, we want to kill the cohomology class of G4 squared. And so if you just add one variable in appropriate degree, namely in degree 7, which kills G4 squared, it turns out that this is enough, and this algebra just has, has a map to the drum algebra. G7 maps to 0, G4 maps to the volume form that you pick, and then it's a quasi-isomorphism. It induces isomorphism and homology, and cohomology.
Thank you.
Yeah, you're welcome. Good question. Yeah, so now relation to physics. So I'm explaining the math physics part of the story. So the thing is that in 11-dimensional supergravity, which is sort of a background theory of M theory has more ingredients, but it's based on 11-dimensional supergravity. There are two basic fields, G4 and G7, and they satisfy the following equations of motion, like this. So these are just differential forms on the 11-dimensional space. This is the Hodge star, the Hodge dual of G4 equals G7, and then there are those two equations. We can actually separate those equations into those which sort of carry a metric information in space-time, namely that one. So I would separate them like this equation, and then those are like metric-free equations. And so we will be dealing with this metric-free background. So to get 11-dimensional supergravity, you work with fields G4, G7, satisfying those equations, plus you add an extra equation. But it's something in addition that you add. Well, you add a metric, which allows you to talk about the Hodge star, and then add this extra equation. And we are working with this background, which is, it's called, physicists also look at it as Sati explained to me, as Hisham Sati, my co-author, explained to me. It's what they call duality symmetric formulations, when you only use those equations which don't include the Hodge star. And so these are the so G4 are the basic fields of 11-dimensional supergravity, and these are exactly the equations of the equation of motion less this equation. Okay, and this is and there is a direct connection because as soon as you have any manifold which has a 4 form and a 7 form on it, and I'm talking about differential forms, such that they satisfy those equations, then there is a morphism to some kind of rationalization over the reals of S4. So this is a homotopy, a rational over R. It's a rational homotopy equivalent space to S4. Oops. So it's rationally homotopy equivalent to S4, but it's some kind of canonical object that you construct out of the differential graded commutative algebra by simplicial methods. And so you create some kind of infinite dimensional complex, simplicial complex, or simplicial set out of this, and take its realization. And this is the space, but it's rationally homotopy equivalent to S4. So in principle, one can argue that there is a map, and there is a continuous map like this, just as soon as you have those fields satisfying those equations. So basically, it says that you can the rational homotopy. If you know the rational homotopy type of the space, you also have a morphism to some canonical object that you create out of the minimal model. So you create out of this object this S4R. But you may argue that there might be like Sati in some of papers with his co-authors, Fiorenza and Schreiber, Urs Schreiber, they wrote a few papers in which they claim that there is actually a map from the 11-dimensional supergravity space-time to S4, not necessarily here. But let me stick with just rational homotopy theory. So rational homotopy theory gives us a map like this to some other model of S4. So that on this S4R, there are differential forms, little G4 and G7, like rational differential forms in the sense of Sullivan, and they pull back by this map, continuous map to G4 and G7, to those fields, well, differential forms G4 and G7 on S4. Okay, and so here there is a direct connection between supergravity and the rational homotopy theory of S4, as you can see. It's a map, and the fields in supergravity are the pullbacks of the generators of the Sullivan minimal model. Okay. Similarly, when we move, let me do just one more iteration. Oh, actually, I'm already talking for 1 hour and 20 minutes.
So you should kind of see what is important from.
Yeah. Sorry, yeah, I got carried away. So let me see what's important.
I just checked. You have like about 6. Yeah, it's quite a while.
Oh, yeah. I kind of thought, looking at your talks, that it was, and I thought you
No. You don't have to stuck with 1 hour. You can go over 1 hour, but some reasonable amount.
Sure. Yeah. Actually, I planned to talk for just 1 hour, but somehow it went longer because we had
too many
wonderful
questions.
discussion. Yeah, which is great. Yeah, and that's what I expected, that it would go longer.
Today, campus is closed. There is no class, so we have an unlimited amount of time.
but I'm not going to keep you
Nobody has unlimited amount.
I'm not going to keep your attention for an unlimited period of time. No, yeah, I will wrap up quickly because this just repeats the previous story, but with the single simplification of S4, and on the other hand, this quotient. So basically, if you had y mapping to S4, then this y, if you mod it out by S1, by an action of S1, if we assume there is an action, so we take y divided by S1, and then it would mean that the loop space, that from this you can obtain an adjoint map to the loop space in S4, because to the cyclic loop space, because basically you see if a point here, roughly speaking, a point on the left-hand side has a copy of S1 sitting over it. It's an S1, a principal S1 bundle, and this fiber, a copy of S1, which sits in Y, is being mapped by this map, which I denote by phi naught. This is phi 1. Is mapped to S4. So this way you get a loop in S4. And of course, since it's a principal bundle over S1, you don't know where it starts. So actually you get exactly a map to the cyclic version of the free loop space in S4. So it's kind of this phi 1 is kind of an adjoint map. And iterating this construction, you get for further reductions, you get further maps to LC squared S4 by the same adjunction. Okay, and then so you get this phi 1, and then you get here we compute the minimal model of the simplification, single simplification, or single cyclic loop space of S4. It may be computed. It's a math question, easy. Another exercise. Well, it's now easy, but it was the subject of a paper, which I will mention on the next slide. And then there is, there is a pullback of the generators to the basic fields of 10-dimensional supergravity, of type 2a 10-dimensional supergravity. And there are equations of gravity, of motion there, and they do correspond to the equations for the differential in the Sullivan minimal model. Okay. So it's very parallel, but you see there are more ingredients, more equations coming in, and you can imagine if you do six iterations, how complicated those fields and equations will be. And so this what I mentioned, that this is a math problem, how to move from, if you know the Sullivan minimal model of a space, what will be the Sullivan minimal model of its cyclification. So in this case, it's applied to k-fold cyclification to get the k+1-fold cyclification. And it's a very simple formula. You just add some generators. So this is a degree shift. You see, V had some degree. V was the space spanned by G4, G7. It was a graded vector space. One generator of degree 4, one of degree 7. And then to obtain this, so the generators, you repeat the generators, we call them, for each generator V, we call them SV with the shift, with a degree shift. So these are those S, G4, S, G7. And then there is an extra generator W of degree 2. I should have written W of degree 2, degree of S, V equals the degree of V minus 1. That's the degree shift coming from that. And this is a formula for the differential, very simple. It's a theorem of Viget, Poirier, and Bourget. Oops. Yeah. So here is, that was an example of, so this is how it works. It was already discussed. So this is how it works when you go from the minimal model of S4 to the minimal model of the one-fold simplification. And now this is one of the theorems, but so the key is, the sort of key idea is that we look at the toroidal symmetries of this of those minimal Sullivan models of iterated simplifications on S4, and therefore of the rational homotopy type of those spaces. So we look at the toroidal symmetries. What does it mean? We look basically at commutant symmetries. So there is this automorphism group of a Sullivan minimal model, which is a real algebraic group for those spaces. In general, it's a pro-algebraic group, but in this case, it's a real algebraic group, which contains, and so the theorem says that this algebraic group contains a canonically defined maximal R-split torus. So we are talking about real algebraic group. So there is this notion of split tori, split over R tori. They look like that, like the real points of the multiplicative group to some power. So the theorem is that there is, for each k, there is a canonically defined torus of rank, dimension k+1. Canonically defined maximal split R torus in the group of automorphisms. So in other words, the torus performs those toroidal symmetries of the Sullivan minimal model of the space. That's the first theorem. We identify and prove that this maximal R split torus is of dimension k+1, and we identify it in a way canonically. Okay, then everything happens in this torus and its Lie algebra. So you take the Lie algebra of this torus, remember the torus acts on the Sullivan minimal model. So the Lie algebra in a way acts as a Lie algebra on the Sullivan minimal model, and then the statement is, another theorem is that this Lie algebra has a natural basis, which gives a lattice in there. You can just span by a lattice by this basis. It has an integral inner product and a distinguished element, the analog of the canonical class in this lattice. And so that this triple, which we associate to the cyclic loop space and its Sullivan model, consists of a free abelian group with a basis like this, a symmetric bilinear form, which sort of canonically defined symmetric bilinear form of Minkowski type. It has one positive mode and the others are negative, k negative modes. It has a distinguished element like this. Well, this doesn't look distinguished because I'm giving you a formula, but the distinguished is being distinguished as a unique element of HK, which acts on the Quillen model by degree. So there is also a Quillen model in the background, as I told you, and the degree basically of the elements in the Sullivan model differ by 1 from the degree of the Quillen model. So I could have just worked with this, but then I would have a shift, which I would have to explain. So that's another theorem. We have those combinatorial ingredients, which are known in the same way as they do in algebraic geometry of Delpez's surfaces, which are known to generate the root system Ek. Like we have all the ingredients to obtain the root system Ek. So this is the second to last slide. For instance, here I'm explaining what the k equals 8 threshold is, where it arises. Oops, that was supposed to be backslash in HK. So this distinguished element, how do you obtain the root system? You take the orthogonal complement in the lattice to the distinguished element, the analog of the canonical class. You take the orthogonal complement using this inner product, and so this is the orthogonal complement, and the roots sit there as basically elements of inner square -2. Well, it depends on how things are set up. Here it will be -2, and the dimension of this HK, the Lie algebra of the maximal split torus is k+1. The dimension of this orthogonal complement is k, and the y. So the roots, if you define the roots by what I said, like elements of the lattice which squared to -2, then it's a finite set if and only if k is less than or equal to 8. And this comes out of the fact that the restriction to this k-dimensional subspace, to this hyperplane in HK of the inner product is positive. Remember, it was a Minkowski inner product or Lorentzian inner product. The restriction is positive definite if and only if k is less than or equal to 8. And so this is this actually implies, in a way, it's some kind of an explanation why the roots form a finite set if and only if k is less than or equal to 8. Okay, and then I wanted to conclude with this conjecture. So let's see. Yeah, I wanted to conclude with this conjecture that, you know, basically we have, remember, we had this triangle: algebraic geometry, algebraic topology, physics, and we kind of completed an arrow between physics and algebraic topology, apart from finding something new, some new series of objects in algebraic topology, which give rise to the EK series. And if you complete one of those two remaining dotted arrows, then you would actually explain mysterious duality. But the mysterious duality originally was duality between algebraic geometry and physics. Now it is duality between algebraic geometry and algebraic topology. Namely, we conjecture that there is an explicit relation between the series of Delpezos and the series of iterated Rook spaces, such that it matches all of those EK symmetry patterns which occur in both series, and also relate other geometric data. Here, I mean, what kind of data, like the volumes of curves on Delpezos surfaces, and some geometric data such as the radii of the sphere S4 and circles for the iterated Rook spaces. And this is all I wanted to share with you.
Okay, thank you very much. Very interesting.
Thank you very much.
Question. Talk. Yeah, actually, yeah. You do you understand correctly that you are able to find the Cartan part of
Exactly.
your Lie algebra inside of the group, or Lie algebra of the group of automorphisms of your whatever Sullivan model. Anyway, some algebra which describe the yeah.
Exactly.
So yeah, indeed. So it kind of looks very plausible that probably if you, I mean, you know that in this Borchardt story, when you have kind of like something like K3 anyway, some generalized, yeah, so you have a collection of vectors in the second cohomology group of some projective surface with certain pairing, and so this is basically corresponds to the Cartan part of the generalized Kac-Moody, but to see the rest of Kac-Moody, you should do something, some extra things. For example, like Gabe mentioned, like realize as a spherical, maybe spherical functors, not necessarily spherical objects. But for K3, probably they all realized as spherical objects. I don't remember. So this is this type of thing. So indeed, there might be some action on DB Koch. Yeah.
Yeah, that would be really exciting. But you're talking again about the action now of the braid group on DB Koch?
No. I mean that it's
when you lift to the total space of the canonical bundle, you expect an action.
Some action. Yeah, yes, some action. I don't know, by correspondences, as sometimes typically happens in that story.
Yeah, of course.
Yeah. I don't know. I mean, I see it for first time, but it's a bit. It's interesting that it's not just action on the cohomology; it's action on the Digi algebra, which gives you the cohomology. So it's
Right.
more, it's some kind of homotopy upgrade. So it's interesting.
Yeah, yeah. It's equivalently, you can talk about an action on the Quillen model, which is actually in this case for those spaces is just the rational homotopy groups.
Yeah,
and the Lie algebra with respect to the Whitehead product. There's a bracket there.
higher massive. Also, I recall, I mean, it's not related to what you're talking, but some strange symmetries of the rational or real homotopy type. Remember this old result of Sullivan about the action of the absolute Galois group on the rational homotopy type.
Yeah.
Yes.
Absolutely. Yeah.
You can indeed find some hidden symmetries. All right, so more questions?
Actually, I have a few questions.
Okay,
Sure.
go ahead.
First is that the M's, I just try to feel whether this Sullivan model M, this looks like to be the symmetric algebra, sort of a symmetric algebra.
Yeah, the graded symmetric algebra.
Yeah, graded symmetric algebra of the graded Lie algebra.
Yeah, yeah.
That's the actually it's the universal enveloping algebra of the graded Lie algebra, and
not
you have this kind of a divided power. And the reason I asked earlier about the Kate resolution, this seems coming from the Andre's work, which says that if you have a Hopf algebra with a divided power, with a differential graded Hopf algebra with a divided power, that has to be a universal enveloping algebra for DG LA.
Yeah.
So is this the Sullivan model and the Quillen's model is in that sense?
Let me see if it's the universal enveloping algebra. No, maybe not quite. It's actually right, because as let's see, right. So it's more like the Chevalier-Eilenberg complex of the Digi Lie algebra, which is the Quillen model. So you take the kind of cohomological Chevalier. Yeah, you take the cohomological Chevalier-Eilenberg complex for the trivial coefficients of the Digi Lie algebra, which is the Quillen model, and this way you get the Sullivan algebra.
And my second question is that whether this earlier in the discussion about how the EK symmetry action, whether this will be something I feel very much like circle bimodule.
Circle what?
Circle bimodule, which
circle bimodule.
Which corresponds. It's kind of a geometric or categorical realization of the Hecke algebra. So when I mentioned about whether it's the var group action or the Brit group action. So whether that's here that you get the kind of a Hecke category in this sense. So this might be a comment or not quite a question. That's what I got a feeling.
That's a good point. It might still be part of the of this derived category business for the Del Pezzos. But again, what will be its analog for those loop spaces, iterated loop spaces? I have no idea. That's a good point.
Yeah, that's where I was thinking of the loop spaces before you take the quotient, or I could not take the homotopic quotient. I will take just the iterated loop spaces, but this time I'll have S1 direct products, copies S1 acting.
Right. Yeah.
So that from that viewpoint, I felt that some sort of closer to the circle bimodule construction.
I see. Okay. Yeah.
Okay, well, thank you very much. This is
Well,
inspiring.
thank you, Jean-Zhu.
Sash, by the way, this diagram E10, which appeared, I mean, it
Let me-
somehow later disappeared because you're talking about something EK, which was K, I mean, classical K.
Right.
up
Yeah,
to
there is
K.
a shift. You know, those diagrams are. I don't know how. I mean, this diagram, those diagrams that I now show. Do you see the slides? The
Yeah.
slide.
Yes,
Yeah.
yes.
So those diagrams, they do correspond to E10, and this is sort of the description of the whole story, like all the objects that show up in the story. However, those diagrams, they go only up to E8, and they are different. So maybe, you know, yeah, there is some kind of shift, but those are different diagrams because for those, I mean, the nature of those diagrams, it's like for each of those BK, you can get this Dinkin diagram of the corresponding type EK. And here, this was like, so each of those gave rise, oops, maybe I should write. So this would give rise to E3, this to E8, and so on. So those give rise to those diagrams. So in a way, one can think of cutting down the E10 diagram, but with a shift. Like if you imagine that maybe we have started with the E10 diagram, but the first cut that we made was here to obtain that E8, and then the second cut here, and the third cut here, and so on. But you see there is a shift. We do keep making two cuts even when there is nothing left. This gives you those two initial steps. So really, there is some mnemonic relation to E10. It's kind of schematic.
Yeah, but it's sort of formal manipulation. But
Formal manipulation.
it has some special religious meaning in the theory of ordinary gravity.
Oh yeah, yeah. But we actually get into E10 in our paper. I just didn't discuss it either. We actually do get to E10. We discuss E9 and E10. You know, those Kac-Moody algebras, which correspond to those.
But so, no relation to this cyclic loop space.
Yes, in relation to the cyclic loop spaces. Yeah, yeah. So you can keep cyclifying, and then you get those affine extensions of the EK series.
Interesting. Because I know that Thibaut Damour told me at HS many times he is very much interested in this appearance of E10, but in ordinary gravity. Oh, yeah, it's interesting. Okay, more questions?
I had a couple of questions. One was what's this sort of rational homotopy version of P1 cross P1? Is this occurring in this sequence or?
Oh, yeah, the rational homotopy version. Yeah, it actually, that's a good point. There is there. We don't know what the space is, but we know the algebra, the minimal Sullivan model. So you can't identify the space to be something as nice, even though, of course, every minimal Sullivan algebra gives rise to a space. You can construct a space, but it's just an abstract space that you obtain from the algebra. And we don't have an identification of it as a nice space, but we do have it in the paper. You can find it. Yeah.
The other question I had was, so all these Del Pezzos have this, beautiful sort of relations to each other by blowing down.
Right.
In various ways. And so do you have like a picture of what that looks like on this rational homotopy side, sort of?
Let's see. So, well, there is always an inclusion of a space as constant loops, but on the other hand, we are taking the homotopy quotient. So there, but still you can use. There is a map like from the space Z to topological space Z to its cyclification by taking the constant loops, by going through the constant loops. So there are maps like that. We didn't find them helpful so far for the time being, but well, we kind of did find them helpful. Right. Yeah. In a way we did. Yeah. Because we're comparing those toroidal symmetries, like iteratively creating toroidal symmetries of those iterated significations. And in a way we were going through that. Yeah. Yeah. Good question.
Gabe, are you happy?
Yeah, very happy. It's great.
All right. Good.
Well,
All
it's
right,
great to have people happy.
More questions? Well, if there are no more questions, Sash, thanks again.
Yeah, thank you for inviting me. And you guys have a wonderful seminar. Apart from the list of speakers that I've seen on the web, you also ask lots of questions, interrupt speakers. That's excellent.
YouTube channel, so you will be immortalized in our
Fantastic.
YouTube channel.
Yeah.
All right. So for the participants next week, I understand it's university spring break, so there will be no seminar. Yeah, next week. But
We
in
have,
2 weeks, yeah, I think we'll have Fabian Heidi. All right. So
we have our spring break this week.
Okay. So
It's
Congratulations.
snowing outside.
It is snow outside. Yeah. Is it snow in Kansas?
Oh, yes.
Yeah,
Today
yes,
is closed
today.
because of the snow. University campus is closed.
Wow.
Okay. All right. So thank you again, Sasha.
Thank you, Jan. Thank you, everybody.